Hello and welcome back. My name is Dr. Mark Taylor. This is Delaware Tech Physics 111 Lesson 5, Part 4. This is part of the second lesson of Unit 2 on forces and energy, and it's a continuation of the sections on Part 2 of the forces. So where we left off, we just finished working on examples of force problems where there is horizontal motion. Now we're going to look at problems with vertical motion. And in vertical motion, you always keep in mind that G is 9.8 meters per second squared. Sometimes you might be told we'll round it to 10 meters per second squared. For this one, it's just 9.8. And we're going to proceed with the problem. But when you were doing kinematics, you were told that you would only see examples where the vertical acceleration is g. Well, we're going to have examples where the vertical acceleration is not just g because it's affected by other forces besides gravity. Okay, let's look at problem number 4. A 4,600 kilogram helicopter, okay, that's the mass, accelerates upward at 2.0 meters per second squared due to the lift force by the propellers. So this is a helicopter. The propellers are spinning and it's lifting the helicopter up against the weight of the helicopter. So the upward force has to be greater than the downward gravity force in order to lift the helicopter up. All right, so let's draw our free body diagram. And free body diagrams for vertical problems are frequently simpler than free body diagrams for horizontal problems. So let's look at it. We know this thing has a mass, and we know that it's being lifted up by propellers. So we've got a weight force straight down, and as always, our weight force is calculated as mass times g. All right, we know the mass, 4,600 kilograms, and we know g, 9.8 meters per second squared. So that'll be easy to calculate. We also know there's a lift force. I'm going to draw it as a bigger arrow because we know it's lifting the helicopter up. And we'll just call that the force of lift. If you want to call it the force up or the force applied, that's fine. But I'm going to call it the force of lift. And the force of lift is fighting against the weight force. Now, are there any other forces? Well, you might say, oh, well, wait, we've always had a normal force, but the helicopter is not sitting on something. It's not on the ground. It's not on a table. It's not on the floor. There's nothing pushing up against it except the lift force is lifting it up. There might be a little bit of air resistance, but it's so minor in this case, we don't even mention it. Are there any horizontal forces? No, there's nothing mentioned. The helicopter is not moving to the right or to the left or diagonally, so there is no horizontal force on this. So it simplifies this problem quite a bit. Now, so when we're filling in our XY table, the X are the horizontals. There is no horizontal force. There's no force in that direction. There's no force in that direction. So we can ignore those. So there's no force there. So our net force in our horizontal direction is just 0. It's 0 because there's nothing to add up. Our vertical forces, we have a positive direction lift force and we have a negative direction weight force. So we put those in. We have our lift force in the positive direction. And I like to put a little positive sign. You can put it before or after the F. Just remember that that positive or negative sign will be added to the number once we calculate any value. Okay, and the weight force, which we can easily calculate, m times g, we know that's going to be a negative force. So the sum of our vertical forces is our positive lift. Let me rewrite that. Our positive lift force, force sub lift, plus our negative weight force. You can draw this smaller to fit in the boxes. And we also know that the sum of those forces will become a net force, or sum of forces, and net forces are always equal to mass times the acceleration. This time the acceleration is in the y direction. You don't have to write that, but you can. But remember, this is your acceleration in the y direction. So you know A, you know M, you can calculate what the sum of the forces is. You can easily calculate the weight. The only thing we don't know is the lift force, and we can solve that from the other two. So let's take a look at the rest of the problem. Calculate the missing force Fg. F sub g, well, that's the weight force. We know how to do that. F sub g equals mass times g, which is equal to 4,600 kilograms times our g value, 9.8 meters per second squared. We pull out our trusty calculator, and it tells us that the value is 45,080 newtons. Remember, forces are always in newtons, and we can assign it a negative charge. What is the missing force sub lift? Well, we have no direct information for force sub lift, but we do know that the force net in the vertical direction is the sum of the force of lift, which we're assuming is in the positive direction. We're not going to put a positive sign in this formula. We assign the positive and negative after we've calculated things, plus the weight force, which we know is going to be a negative force. We already calculated the weight force, so we can substitute that in, and we know the net force is going to be equal to m times a. So we can put m times a in place of the net force, and we can put in lift here, which we don't know, and then we add it to the weight force, which we know is m times g. We've already calculated that. And now we basically are plugging in numbers to calculate the rest of this. We have mass is 4,600 kilograms again. Looking at the beginning of the problem tells us what the acceleration is. It's 2.0 meters per second squared. So we go back, we plug in 2.0, whoops, let me move that a little bit. 2.0 meters per second squared. That's our acceleration. So that product is going to be our net force, and we can calculate that. That would be 9,200 newtons in a positive direction because it's going. Because it's the sum of those forces. It'll be 9,200 newtons, and we know the acceleration is in the positive direction. And that's equal to the lift, which we still don't know the identity of, plus the weight. Well, the weight force is negative 45,080 newtons. Well, now we have to add 45,000 to the 9,200. We add plus 45,000 to both sides, 45,880 to be exact, newtons to this side, and we add 45,080. That's now plus because we're adding the positive version to both sides. That cancels, and we're just left with lift equals the sum of those two terms. Well, we add those up. So I'll just write it over here. The force of lift is the sum of the 9,200 newtons, which we know is our net force, that's positive, plus our 45,080 newtons that we just finished calculating. We add these two up, and we find that our lift force is a whopping 54,280 newtons, and that's positive. So that's our lift force, and that completes that problem. Okay, looking at the next vertical motion problem, we have a slightly different setup here. You'll notice that in this problem, you are asked to use a rounded value for G of 10, and even 10 meters per second squared. And this will make your calculations actually much, much easier. So let's just use that for now. All right. So this problem states that Tyrell jumps from an airplane. Presumably he has a parachute. Okay. His total weight with a parachute is 840 newtons. Okay. So I really want you to get in the habit. The second you see a mass, calculate the weight. And in this case, the second you see a weight, calculate the mass. So this value is his weight. It is F sub G for Tyrell and his parachute. All right. And we know that's equal to mass times gravity. I assure you this will be a good thing to do on the side. Calculate the mass. Remember, force of gravity equals m times g. So what you're really doing is taking the weight and dividing it by g. So you're literally taking 840 newtons of weight and dividing it by 10 meters per second squared, which you can do without a calculator. Hopefully you know how to divide by 10. You're literally just moving the decimal point. And that's 84, and the units for mass are kilograms. So his mass is 80 kilograms. I'm sorry, 84 kilograms. And this will probably be of use to you later in the problem. So keep that in mind right away. All right. Draw 3 free body diagrams for Tyrell at the beginning, the middle of his jump, and when the net force is 0. So the idea here is Tyrell's jumping from a plane, and the second he jumps from a plane, what force is on him? Well, he has a weight. Just because there's no ground doesn't mean he doesn't have a weight. His weight is m times g, but you were told what his weight is. It's 840 newtons. That's his weight. Is there any other force on him at this point? The moment he jumps out of the plane, there's no other force except the force due to gravity on him, which we call weight. As he falls, his speed will build up in the air. He will rub the air more and more, causing friction with the air. And we call friction with the air, we have a phrase for that. We call it air resistance. We also call it drag. So drag or air resistance would be an upward force. But the instant he jumps from the plane, he hasn't built up enough speed. He hasn't built up any speed that in that instant to start rubbing against the air and creating air friction, air resistance, drag. So as he falls, he still has a weight. The weight never changes. His weight is not changing as he falls. It's always going to be 840 newtons. But what's also happening is now air resistance is starting to build up. And I'll abbreviate this as force sub R for resistance. And eventually he'll fall faster and faster, and the air resistance will build up. It will build up to a point where eventually the air resistance will be exactly matching his weight force. That is, his air resistance eventually will be exactly the same value as his weight force, but in the positive direction. So remember, this is in the negative direction always, because it's down. And this is in the positive direction because it's up. And these are our three free body diagrams. Now you might ask, well, does the air resistance build up any more than this? Well, it does not, because at this point, there's no net force in his body. He stops accelerating, which means he stops going any faster, and he can't rub against the air any faster. So that's the last air resistance value you're going to find until he opens up his parachute. All right. So question B says, at the instant he jumps, so that's this free body diagram, what is the air resistance on his body? Well, at this point, he hasn't started moving downward at that very instant, so his air resistance is 0 newtons at this point. All right, let's look at part C. At the instant he jumps, so again, this is this free body diagram. At the instant he jumps, what is his acceleration? Well, I could go through a calculation, but there is a way to use simple logic on this as well. The only force on him at this point is the force due to gravity, and therefore that is by definition free fall. Remember, free fall is when only gravity is the only force on you, and therefore the only acceleration that you will experience is g. So its acceleration at this point is simply g, which we're rounding to 10 meters per second squared. And now we have to point out that it's in the downward direction by showing a negative sign. So that's his acceleration at this point. If you wanted to actually calculate it, what you'd have to realize is that for that situation, his net force in the vertical direction is the same as his weight force. Well, we know his weight force is m times g, and we know the net force is m times a. Well, then all of these are equal. If m times a equals m times g, then a must equal g. But if you just use logic and say it's the only force on him, so the only acceleration on him is g. Okay. Scroll down just a tad here. Part D. Soon after jumping, his resistance builds up a little bit. So now we're talking about the second free body diagram. I'll scroll back down just a tad. Okay. It builds up a little bit, and his acceleration becomes half of his original acceleration. In other words, A is half of G, half of what it used to be. What is the net force on him at this point? Well, you're told that A is half of what it was. Well, what it was G. So now you know his new acceleration is half of G. You know that net force, as always, and it's in the y direction, but I can just say net force, equals m times a. But a is equal to g divided by 2, or 1/2 of g. So therefore, his net force must be equal to m times g divided by 2. I just rewrote that. Well, mg divided by 2 is his weight. Mg is his weight divided by 2. Well, he weighs 840 newtons. Divide by 2. And that gives us a value of 420 newtons of net force. But remember, it's in the negative direction. It's pointing down. So our net force is negative 420 newtons at this point. Okay. Looking at the next part of this problem, what is the force of air resistance at this point? Well, we know that at this point, we have a weight force pointing down. We have an air resistance force pointing up. That's the force we're trying to calculate here. And we know the net force is the sum of those two forces. It's the weight force pointing down, that's a negative value, plus the air resistance force pointing up. And we know they add up to negative 420 newtons. That's what we just calculated. Okay. We know his weight is negative 840 newtons, because that's also pointing down. So the only thing we don't know is air resistance. So his weight is negative 840, and his net force is negative 420. If we move the negative 480 to the other side, that means we're adding 840 to this side, and we're adding 840 to this side. 840 newtons here cancels out, and that leaves us a total of our air resistance. I probably should have given more room here. Air resistance is the sum of these two numbers, positive 840 and minus 420. Well, that's positive 420 newtons. Now, you can calculate it like we just did, or you could use logic and say, okay, the air resistance is balancing half of his weight because the acceleration is half, so it must have canceled half of his weight, and therefore the air resistance is half the weight, half of 840, but it's in the positive direction, and therefore it's positive 420 newtons. So when the calculations are fairly easy to do because we're using 10 for gravity, 10 meters per second squared, you can do this math with just simple logic almost as quickly or even quicker than using a calculator. All right. Part F, at what force of air resistance would his net force be zero? Well, the net force is equal to the sum of his weight force, which is pointing down. I know I've written it in different ways here. It's the weight force pointing down plus the air resistance force pointing up. If that's going to be zero, it means that the air resistance must be exactly balancing his weight. Well, if the weight force is negative 840 newtons because it's pointing down, that means the air resistance force must be positive 840 newtons to balance it up. So part of the reason for giving you very little room here is to use logic instead of formulas, but I wanted to show you the formulas as well. All right. G, what was his acceleration be at this point? In other words, at the point where the net force is zero. Well, remember, if net force is zero, then acceleration is zero, and vice versa. If you know the acceleration is zero, then the net force is zero. If you know the net force is zero, the acceleration is zero. What would be true of his velocity? Well, several things would be true of his velocity. The first thing is, since the acceleration is zero, it means there's no change in velocity, therefore his velocity is constant. Absolutely is constant. Now, a lot of students look at this and they say, oh, it means he stopped. No, it doesn't mean he stopped. He's still moving downward. So the velocity is downward. He's still moving. And not only is he moving, if he hasn't opened up his parachute, his velocity is very fast. In fact, a typical human being jumping out of an airplane reaches this speed and doesn't get any faster, but they're moving very fast. They could be moving in the ballpark of 120 to 150 miles per hour at this point, straight down, depending on how big they are and the wind the wind pressure, etc., etc. Well, when the velocity is constant, it means it's not going to grow anymore. It's gotten as fast as it can possibly get. It's stopped growing. So we call this the terminal velocity. And you may have heard that term, terminal velocity. Some people will call it terminal speed, but it's the terminal velocity. Terminal velocity, terminal doesn't mean zero velocity. It means the last velocity. It's as fast as Tyrell's going to go out the airplane. And this completes this problem, but I want to point out, once Tyrell actually opens up his parachute, I'll draw a free body diagram for that, you have his weight force pointing down. That does not change. His weight is not changing. But the moment he opens up his parachute, the parachute provides a tremendous amount of surface area that catches a tremendous amount of air and creates a tremendous amount of friction with that air. So the air resistance suddenly becomes a gargantuan number. And now his net force, if you add this negative value to this giant positive value, his net force is going to be very much in the positive direction, bringing him up briefly, and then he'll float down at a much, much slower terminal velocity, which is easily survivable. But unfortunately, this value without a parachute is just not survivable. Okay, well, this concludes the required portion of Lesson 5. The remainder of Lesson 5 is an advanced section that discusses the use of some trigonometry and the Pythagorean theorem to analyze forces that are not directly vertical or directly horizontal. That is, they're somewhere diagonal pointing, and they have to be broken up into component forces, what we call horizontal components and vertical components. And that's another discussion. So we'll end here.